though still a little bit clumpy. But look at how many connections have formed. In some areas, it's almost a solid mat of twisted dendrites. I hope this gives you an appreciation for just how complex your brain is. This is what a few thousand at this point actually. I hope a single shattered snot understand now galactic web. Not only can you see the incredibly dense network that has already formed, you can even see what looks like synapses. And the incredible green color means they are all very healthy. At the highest density, it's more of the same, but you can get a better idea of what the blobs look like. They're made of a shell of neurons which maintain neurons and keep them healthy. Now, let's jump ahead a few days to day 10. At this point, things were getting a little weirder. The cells were still healthy, but we were starting to see some really big chungus-looking blobs forming at the highest density. So I think it's safe to say that the highest density is too high for our experiments, as these blobs won't sit on the array properly, but they do look cool. At medium density, things looked better, though still a little bit clumpy. But look at how many connections have formed. In some areas, it's almost a solid mat of twisted dendrites. I hope this gives you an appreciation for just how complex your brain is. This is what a few thousand neurons do. Imagine how many little wires are in your head. The lowest density at this point actually looked the best, with a nice network forming but very little clumping. And that trend continued onto the final day, where they had formed a beautiful and dense network with very little clumping. So I think the verdict is that the correct seeding density is probably around 15,000 cells per square centimeter, just a little bit higher than the lowest density. Now, let's talk about the arrays, how they'd fare through all this. Well, there's good news and bad news. The good news is the neurons adhered properly and did grow, at least a little bit. Bad news is threefold. First, we can't stain them because we'd have to break the arrays to do that, so we can't use our nice indicator to see if they're healthy. And second, I think that there wasn't enough airflow. Because the lids thread on, even when loosened, I think they have a tendency to seal and prevent oxygen from getting into the cultures, so the neurons eventually asphyxiated. Finally, while the little windows on top worked to let light in, it was still pretty restrictive of the area we could look around. So for next time, we're probably going to make custom vacuum-formed lids that will both let in more light and more air. But otherwise, I'd say this has been a big success. We can definitely now grow neurons and keep them alive in culture, which means we can check off the first step of our tech tree. So where do we go from here? Well, let's wrap this video up by talking briefly about what's coming up in the series. If we look at the main quest line, you can see that next up is getting signals out of the arrays. This means we'll need to finalize the array design or buy a commercially made one, and finish our electronics. We already started building and testing that side of this project, and currently plan on using this amazing little chip, which is a purpose-built neuron amplifier. It's made by a company called Intan Technologies, and they have chips that either only do recordings, or chips that do both recordings and stimulation. So we're currently looking at buying the head stages from them, which include the chip, and then building our own backend for it. That said, if you're from Intan and you're watching this and want to send us one of your lovely complete systems, we would be happy to show it off and use it. Beyond that, we have a set of side quests, which I mentioned near the beginning of the video. One issue is that neurons are really expensive, but also they don't divide, so you have to buy them every single time you need them. What would be much more convenient is if we could just grow them ourselves, and while blending a pet store rat might work, there's a much more elegant way to get neurons. By far the most interesting way is to start with skin cells, and then using a combination of DNA and small molecules, you can directly convert those skin cells into neurons by reprogramming them. There are pre-made kits that just let you do this, which you can just buy, but if you're already making new neurons, it opens up another interesting possibility. Neurons grown in a sheet, like we've just shown, aren't exactly a perfect model of brain physiology. While they still can learn and form connections, they don't have any of the intricate structure you get in a normal brain. But there's a technique which grows tissue that is much more like a real brain, and it's called making organoids. Basically, you purposely grow balls of tissue, just like the big chungus we made by accident. But because you're starting from a stem cell-like state, the cells start to organize themselves much more properly into tissue that looks more like real brain, behaves more like it too, and even